we have seen CV characteristics. So now the other property of any device, one was CV, the other is IV, and we are interested to know if I apply bias across the PN junction, and let's say I apply positive potential here and negative here, or ground here and positive there, P getting positive voltage, N getting negative voltage, we say this device is forward biased. This device is forward biased. However, if I apply negative potential to P region and positive potential to N region, we will call this as reverse bias. And we have seen in reverse bias, the PN junction acts more like a capacitor. That's what we monitored the CV. And then we said, however, we did not know how much current in reverse bias it was flowing. We didn't know in case we forward bias the device how much current it can provide to us. The earlier part was capacitance voltage was essentially used as varicap or varactors. However, this device can be used as a what we call a switch, and we want to know if I apply some potential here, say positive negative, I expect as if switch is on, the resistance here is very small, preferably short, or if I apply reverse bias, negative potential here, positive here, then I expect switch to be open as if, or to say RR tends to infinite. This is essentially what diode will act under forward bias and reverse bias. And we already seen earlier that a switch can be replicated as if at V is equal to 0 or just V greater than 0 when the device becomes forward bias. The current should be as large as possible, limited by the circuit. And under anything V, this is V greater than equal to 0 and V less than equal to 0, the current should be 0 ideally. This is called the ideal switch, that I want no forward voltage drop, I want no all reverse bias, any voltage I apply, current is 0. That is open circuit and short circuit. This is what I expect. But however, when I actually try to use this diode or device, I figure out that initially there is a small current even if I apply forward bias, until certain voltage, which we call cut-in voltage, the current still is very small and then starts rising exponentially. As we start increasing forward bias beyond V gamma, we say the current starts increasing exponentially, and that when we reach a very large current level, which we call high injection level, the current starts rising. So this has a relationship e to the power q Vf by kt. If Vf is a forward bias, this has e to the power qf by 2 kt. And beyond this, the current saturates, or not really saturates, it increases a little bit, which is called resistive region. The diode acts like a resistance at very large currents. And we also see in this small region here, it also shows a relationship. This is all proportional. E to the power qvf by 2k. So initially we see in the forward bias, when the voltage starts increasing, the current increase is e to the power qf by 2 kt. Of course, its pre-exponent term may be smaller and therefore the value is smaller. And as I increase forward bias, let's say I reach some value called V gamma, I find suddenly current starts shooting, which is proportional to e to the power QBF by K, exponential rise. You can see typically at temperature of 300 degree Kelvin, KT by Q is 25 millivolt or so, or Q by KT is around 40. A small value of VF, let's say even 0.1, 0.5 volt, this e to the power 20 is the number you are getting. To increase little bit more, exponential term will further increase. That means the current starts really shooting up. This is exactly what switch was expecting, that as we increase it, the current starts to go to as large as possible, creating a short circuit equivalent. So we see here that somewhere at crossing V gamma, so instead of this reaching at this, one can ideally say, okay, it has a characteristics up to V gamma may be zero current, and then at V gamma it starts giving infinite current. So equivalent circuit, now I know there is an offset voltage up to which there is no current. Beyond that, we are still having a switch kind of characteristics, and we say we are replicating a switch. Why are we interested in switch characteristics? Because all our digital hardware thinks 1010. So I want to see whether diode can be used as a switch there. However, later we'll see it's not so easy, because there are only two terminals and you don't have any control. You only can change the polarity. Okay. That is plus minus. You can do switch like this. So, and we want to have another control, and therefore we came out with second device, which was called transistor, where the third terminal started controlling on-off currents. Otherwise, diode is as good at switching elements as the transistor is. However, we see if I go beyond certain current level, we figure out the current starts again slowly rising. E to the power Q by 2 kT rise starts. This is called high injection level. The earlier one, this region, is called low injection level. Injection means available carriers. This is high injection level. And if you further increase the current, what does that mean essentially? If you increase too much of carriers, both on P and N side, it doesn't remain P or N, it becomes universal as if equivalent of P and common everywhere. Okay, it's like a resistor, standard resistor. So if large current starts flowing, the diode will act like a simple high resistance value. Now this phenomena which we observe, of course, is experimentally verified, and we'd like to put some theory why such, okay, and we also see, as I say, initially this Q wave 2 kT, here also 2 kT. But the phenomena of the high injection is altogether different from phenomena at extremely low injections. That is very small VF values. It still show e to the power QF by 2 kT. Very high also it shows this, but the two phenomena are nowhere close to each other. They are very different. We would like to know what are those phenomena. However, most of the time we will work, our device will get biased somewhere in this voltage regions, in most circuits, and most of the time e to the power Q by KT will be the proportional, in most cases. However, the characteristics must be known why initially something like this, then rise, and then why it shows so. If I apply reverse bias, I figure out by one theory, I say current initially rises a bit and then remains constant. Whatever voltage I apply, reverse bias I apply, the current does not change. But in reality, we do find, that means what is the resistance if the device shows constant reverse current, very small but very constant current. What is the resistance I am talking about? Infinite kind or large resistance. Now we see in reality this does not remain constant, but it does change a little bit. Of course I am expanding it intentionally. The current does rise as I apply reverse bias. Though first theory says it should remain constant, but in reality I find it does not remain constant. So there is another theory must be put why this current is not constant but additional current is coming from there. So there are two phenomena even there we are looking for when the reverse characteristics is seen. This is what the theory is all about. That means this part of the current essentially is independent of voltage, whereas this, of course slowly, is a function of reverse bias. Is that clear to you? Now though it happens very interesting, so whatever pre-exponent I get in this current, let's say this value I call it say I saturation. The relationship here does show a very interesting result. In reverse bias, let's say the current is minus Is, and in the forward bias, IC this Is value is same there and same here. So phenomena wise, reverse bias Is is not same as forward bias Is, but the term which you get at the end of the day is same. That makes us very interesting because if I say now instead of Vf, V is minus Vr, if V is minus Vr, that is reverse bias I apply in this equation, then IR will become Is e to the power minus QVR by KT minus 1. If VR is large enough, e to the power Q by KT into V will be very large quantity. E to the power minus large quantity is close to 0. So this is minus Is. So except for small VR, when the current starts rising, rest of the place you see constant current can be seen, which is same as from the forward bias. Okay. And that's interesting. That means I don't have to really evaluate Is. When I reverse bias, I know reverse saturation current, which is Is will flow. Opposite direction because polarity will be opposite. Now this means this equation, call it IF or I, could be used as a universal. Maybe you call it applied. I is equal to Is e to the power QVA by KT minus 1 is a universal diode equation. And to make this slope changing, I may also add one term n, where n can be 2 or 1. N can be 2 or 1. E to the power 2 KT means n is 2. E to the power QV by KT means n is 1. Now this n is called ideality diode, ideality factor. It is also a function of material, how much is, whether it is silicon, germanium, gallium arsenide. It also is a function to some extent of the dopings, but right now assume it varies between 1 and 2. This means once I have written a relation I is equal to Is QU by NKT minus 1, then as far as the circuit part equivalent if I derive from there, I don't have to worry too much. Because once I say, okay, this is general equation, I find equivalent RF, RR from this, or resistance, capacitance from this, then that model is universal for forward as well as reverse. So this is for the circuit people. We want to see how do we connect to a circuit person. But still it doesn't satisfy us. Arey Baba, n related to 1 etc. What's the cause? It must satisfy us, yes, these values are possible by understanding of the device physics, and that's what we now do. So this is circuit part. We'll only use this relationship in deriving the equivalent circuit, but we will be actually trying to know how it varies and why it varies, or in the reverse bias, why current, what does that mean? RR is not infinite, but RR is finite, large enough, but finite. Finite means, as I just said, I want to be infinite. Ideally it looks to be, but it's not. There is a finite RR value. Same way, this current doesn't shoot infinite way. Therefore, it has a forward resistance. So what should be a good diode should be RF. For a good diode, I want RF tends to 0. Typical value may vary from 10 ohm to 100 ohms or even lower sometimes, depends on the dopings I use. And RR, if it tends to infinity, typically this value may be 10 mega ohm to even some cases 100 mega ohm. Why these values are needed? Because for circuit, I must know the equivalence. So values typically which I am getting in a circuit of a diode under forward bias is something like few ohms, 10 ohms or sometimes even 1 ohm. Sometimes even it is less than a ohm if you design it properly. But always think of it, if I am trying to achieve something much better, I may be giving something else. That what I lose in case I want to reduce or increase either of them. We also see if I keep increasing the voltage in this reverse bias, at certain value, call it say breakdown, the current starts. That means device short circuits as you cross that value called breakdown. In reverse bias we say okay, depletion layer is enhancing, more and more electric field is created and therefore very few carriers really can go. Is that clear? And therefore practically zero current or very small current flows. However, if you keep increasing reverse bias, it doesn't remain so. With certain value of this, it suddenly starts shorting. This is called breakdown. This breakdown device makes it device, what is the maximum reverse voltage it can stand is called its breakdown voltage. Is that clear? Typically it can be 30 ohm for a transistor junctions, 25-30 ohms, and a good diode may have 100 ohms and good power rectifier, 100 volts, and good power rectifiers can have as much as 5000 volts. It's called power rectifier. While all transmission systems will use converters, rectifier is named converter if you take a course in machines. Inverter, converter. Converting AC into DC is called converters. DC into AC is called inverters. Okay. Basically similar. There also we use diode. Here also we use diode. There we may use a modified diode which is called silicon controlled thyristors or resistors, SCRs. Okay. But they are still diodes. Okay. Still diodes. So this fact that there is a limiting voltage in the reverse bias up to which you can work, okay, and what is the phenomena. Now it has been found, why I am interested to know phenomena, that some diodes IC breaks down as low as 2 or 3 volts or 4 volts or even less than 2 volts. That means as soon as you reverse bias, little voltage and it short circuit. This breaking down of a diode at a very low value, this value is named Zener voltage, VZ. So there is a mechanism of failure or breaking down at very low voltage of a PN junction in the reverse bias is called Zener breakdown. The one which is larger one shown VBR is because of the phenomena which is called avalanche breakdown. So we will also see the breakdown characteristics of a diode. There are 3 voltages one observes in PN junctions. One of course is avalanche breakdown. And one, the word itself suggests there are avalanche of carriers coming and therefore large current flows, avalanche, like in Himalaya or any other this, suddenly the ice breaks down and huge amount of ice converts into water and then you have a deluge. Same phenomenon, avalanche. The second of course which I have shown is Zener, which is honoring the Zener, not double N, Zener voltage. This has to be less than 3 volts or 3 volts. This is Zener is not having However, in your lab, I hope so you have already used it. A Zener diode in many circuits they are having a Zener breakdowns of 5 volt, 8 volts, 10 volts. They actually say 8 volt Zener. So actually those Zeners do not follow the Zener breakdown mechanism at all. Typically, I can adjust my breakdown somewhere here, okay, which does not follow the mechanism of Zener. Okay. But the values are comparatively smaller, 5 volt, 6 volt, 10 volt, 8 volt, whatever value, most volt, these values are available to us in markets. So the third is, the phenomena which will allow me to do this is called punch through. This is called punch through breakdowns. All Zener diodes marketed in the market, all those who are available in market are essentially non-Zener devices. They have breakdowns of 4 volt, 5 volt, 10 volts maximum, and they are sold as low as 5 rupees to 15 rupees. Whereas the Zener diode per se, if you buy, it may be $160. So you can imagine that obviously if they would have been the same, they would not have been the cost differential of it. Whereas the normal diodes, which we use in most cases, converter applications, have avalanche breakdown mechanisms, but many of the power devices tells, oh, I want a breakdown of 2300, okay, or 4000. Then I may not use the avalanche mechanism, but I see it is punch through must occur prior to avalanche. So punch through can be adjusted to as low as 5-6 volt and can be as high as 1000, 2000. So most power rectifiers are not avalanche breakdown devices but are punch through devices because they want to know maximum how much voltage I will sustain. So all power devices you see in the market are punch through devices. Therefore I say punch through is more dominant phenomena rather used device than avalanche and Zener. But essentially we must know why these three are different. Okay. This is what essentially it means, that I must study at least what are these three mechanisms. Most interesting among them is this. Second may be this. And this is the least interesting to explain. This is much easier to explain, but that's the dominance. Okay, so let's go back to do some theory. We have said enough of it. I have seen experimental results and now I want to verify, can I put a model? So I always say all device physics people, they actually they never create a theory first, sometimes they do, Shockley's do, but otherwise, even Shockley, the first transistor theory came because Bardeen Breton showed something happening. Okay. So obviously the modern people always try to see what measurement has given, maybe wrong sometimes, but they will put all theories on it and later on someday come to know that, for example, there is a very recent, 10 years, 15 years ago, there was a famous research called high TC. The superconductors was found at as high as 77 degrees plus, that is 80 degrees Kelvin or 90 degrees Kelvin. Gaga, everyone, so many people started thinking they will get Nobel Prize now and everything. Suddenly some fine day, someone said, oh, this is all humbug. The result which they are showing are not correct because the way they measured itself is wrong. And whole theories were created why 80 degrees you can get a superconductor. But realized point that nothing was there. Same way another thing happened is called cold fusion. A lot of chemistry people suddenly thought, including our big shot in India, he also thought, oh, this year's Nobel Prize for him. There was a huge conference in Utah where some 100 people came and 80 said this is humbug and proved it. Everything went on. So, device people का क्या है? कुछ भी result हो, हमारा theory. So let's put हमारा theory. Okay, so let's first start with, there is a famous story, just to keep you away from device. The things happen whether you like or you don't like, or whether you understand or you don't understand. There is a famous two Nobel Prize winners, I think you might have read this story, very famous old story. Pauli which states the Pauli's principle, exclusion principle, and his big boss Bohr. Once Bohr was in his Belgium home, and those in India, of course, not so easy, but there they have farmhouses or whatever old village house. So Bohr was in his village house, so Pauli came from Munich to meet him. So as soon as he was looking at his small house, there was that horseshoe was put up on the door. So this man, young man, Pauli was that time 27, he entered very shouting like, Bohr, I never expected a man of such eminence in physics believes that this can help. So Bohr's reply is very important. He says, oh Pauli, I also don't believe, but my villagers tell whether you believe or not it works. So device also works whether you believe or you don't believe. Okay. So let's start with ideal IV characteristics. So let's see, following, I think some points I noted down from which book, the other one, Niemann's book, so I just wrote down. The first thing they say, assumptions. This is taken from Niemann, so you can note down or note down, but just to repeat. The first thing they are saying, under bias, reverse or forward, these depletion regions, either cases, their boundary is sharp. Is that correct? The first assumption we are making, depletion layer boundary is sharp. Sharp means what? This and this. Beyond that there is no depletion, beyond that there is no depletion. Depletion is universal in that region. Just uniform and steps down as the, what are these regions called? If this is depletion layer, what are these regions called? Neutral regions, because there is no electric fields should be possible. Should be, but let's see why. So we say, first thing he says, that is very short. Second, they assume low injection. That's what we are looking at, low injection. The first theory is for QV to the power KT minus 1 fine. So let's see this. Then we assume, which is not every time correct, Boltzmann statistics valid. In non-equilibrium, we have said Boltzmann statistics is not valid. But how did we allow it to happen? Which method we say? Using quasi-Fermi levels. We said, okay, we'll still use it. So that essentially means we'll use quasi-Fermi levels in steady states. Okay. The fourth and the most important property of any device for that matter, and diode is specific here, the total current is constant. For a given bias is constant throughout the device. This is most important, throughout the device. Which means, if this is, let's say, a device, then let's say one current is something like this, the other current is something like this, so it must be some constant current J must flow, and at different points the electron hole current may not be same, but the total sum of them must be constant for get total current. So J is universally constant in the device. Every space point J is constant. Is that correct? From end to the first to end, J is constant. This is very important assumption because let us say I know J and X. So what will be this? So I don't have to derive the other one. I say if J and X is the current I observed, J minus J and X must be JTX because that's what we say K is constant. Okay, so this is something which we'll use in getting the other currents, not necessarily every time we will derive both. So constancy of current is very important in derivations. Also, very important thing we assume, all currents are continuous. Now this word is very important, which means, I should have said, it should not happen that this is your junction, the current in this side is this, and then it becomes like this, and then, no, it must have somewhere. Current should be continuous throughout the device. It should not say that there is no current here. Current must be continuous throughout. This is another. Now it's not really assumption. This, if you don't do this, whole theory will collapse. So this is very important. The last but not the least, we also assume to start with, in ideal case, both electrons and hole currents are constant in depletion layer. Just make out. I already made it. In the depletion region, electron and hole currents do not change. What does essentially I mean by that? There is no recombination or generation recombination term present in depletion layer. Whatever is injected or received should be passed. So the last assumption, we will modify this because this part probably then cannot be explained if we don't assume the other one. Okay, but initially, as I say, which area I am looking for? This area. Therefore, this assumption may be quite good. So we say both electron and hole current are constant in depletion layer. So in future maybe depletion layer I may call as DL. So in depletion layer, these are the assumptions in deriving the expression for I is equal to Is e to the power QVF by KT minus 1, that the current relationships we wrote earlier. We want to prove this, can we get that expression? How much is the Is value and why it shows e to the power QVF by KT relation. So have you noted down, these are the 6 possible assumptions. They can be more also, they can be lesser also. One can derive, if you remove any of the assumption, the complication starts. Since we are looking for ideal, we assume. Then what is the method we apply? You remove one, add something. You remove second, add something there. This is what modeling we do. एक एक assumption को बाहर करते जाएंगे, उसका कुछ टर्म ऊपर जोड़ते चले जाएंगे. Maybe with this course whether we will be able to do all of it, I'm not sure, but let's do that if possible. Okay, so let's start with device under forward bias. Is that okay? Should I rub it off? Okay, so here we start. We have said V0 or in other book it is BBI, built-in voltage is KT by Q, ln NE ND by NI square, where I am taking a case of a PN junction. Okay, now first thing first, physics say what will happen. Initially you have a built-in voltage V0 which is giving an electric field, call it E built-in this direction, positive to negative. Electric field always, field lines start from positive terminal and terminate at negative terminal. So electric field is starting from, this is plus minus. So, however when I apply positive voltage, that is this positive and this negative, it is as much as saying I am putting another battery of VF. Is that okay? Now our assumption, another assumption which I should have written, this voltage drop appears across only this space charge region. In reality it should drop somewhere here as well. But our assumption to start with, all this voltage is appearing across the space charge region or the junction. If that's so, what is the voltage you will get from this? If two batteries oppose each other, they will subtract. So the net bias from this is V0 minus. Now questions could be raised before we go ahead. How much Vf it could be? So the way is, if you start increasing Vf too much and close to V0, the currents which you will get will be as much as 10 to the power 80 or 10 to the power 90 kinds of things. By then the device will heat so much, it may not be there, it will be above it. So obviously Vf cannot exceed V0. But externally no one can stop me putting 100 volts or even 5000 volts. Is that clear? Internally the device cannot get voltage more than V0 to keep device forward bias. And if that is so, where else the voltage is going? So somewhere the remainder voltage must be given. Which regions it can then drop? Yes, it may drop here, it may drop here, it may drop at the junctions. But the diode junction will only get Vf, which is less than V0. If V0 and Vf are equal, there is no junction, everything can pass. Resistance, that's exactly what happens. When you come closer to V0, is that clear? V0 minus Vf is 0, which means no barrier, everyone can go anywhere, like a resistor. Okay. So there is the limit essentially will come. Okay. So the all forward bias say, even if you apply any external voltage, Vf will be always less than this. So initially what we'll say, low injection means low voltages. We say there is no voltage drop here, there are charge neutral regions, there is no space charge here. Therefore all that voltage will occur is across the junction and the net voltage will be V0 minus 0. If that is so, before we go to this, let us say this is our band. Okay, this was our PN junction under equilibrium. EFN is equal to EFP, EIP, ECP, EVP, EVN, EI. You can say I am not so. This is under equilibrium. And what is this voltage? Band bending. Okay. Same way EI, this may not be shown properly, but even EI will have same bending. So everywhere the band bending shows the built-in voltage. But now you say this is the value for built-in voltage. Is that clear? This is the value for built-in voltage. But if I apply forward bias, now I am saying the barrier is reduced to V0 minus Vf. Physically what is happening? If I apply negative potential to N, minus QV is what? Energy. So electron energy is getting enhanced, increased, with reference to what? The P side. So what this shows essentially means, if this is going to be minus like this, that means essentially we may say, maybe we'll redraw this part at least. We may say now, not exactly. This is EFN, this is EFN, and this voltage now is QV0 of energy. So what has happened? These are parallel, huh? Somewhere if they don't show, don't keep it. Since you say it is V0 minus Vf, the conduction band of n side up went up, Fermi level corresponds to what in steady state or in Boltzmann statistics? This related to EC position. Is that clear? So if n has to be this must move upwards. Is that correct? But P we haven't changed. So P remains separated as they were. So the difference between these two values is also how much? The applied voltage. If you would not have applied voltage, they would have been in the same position. As soon as you apply forward bias, they split. So splitting of Fermi levels in quasi states is essentially measure of applied voltage. So this value is nothing but energy difference is nothing but the 2 years. Is that okay? At zero bias, no current was there, EF were aligned. As soon as you apply, the conduction band went up, so Fermi level there went up. This remains. The difference came as because of applied bias. So splitting of Fermi level, so EFN minus EFP is essentially measure of applied. Is that clear to you? This is very interesting. If that is so, that means once I know the position of Fermi levels, now I can find the relationship of n, earlier n and to earlier that it was in steady state or it was in thermal equilibrium, and after split, okay, that carrier concentrations I can now relate from this band diagram. Once I know, oh, they are changed, then I will be able to use statistics. Which statistics do you want to use? Boltzmann, because I said this is my assumption. On the N side I will use, on the P side together I may not be correct, but as far as each side is concerned is steady state. So what essentially is making this to happen? If I say if this potential barrier is reduced, earlier when there was no bias, or equivalently say zero bias, the barrier was very high. So, and why this barrier was created? Because some of the holes went to the N side, some of the electrons went to the P side and opened up phase charge. And they continue to do so till this electric field stops whole electron transport across. That's what we define as built-in field. Now you have reduced that net potential barrier. So obviously now we'll see, oh thank you very much, I have smaller this to climb now, okay. So now more holes can come here, more electrons can come here. As soon as holes move from P to N region, on the N side, and let's say assumption is low injection as I said, the amount of carriers which N side receives holes are much smaller than the N concentration here. What does this essentially mean? Holes are still in minority in N region. Same way I say electrons reaching on the P region are still in minority compared to the holes in the P region. Is that clear? As soon as you see minority carriers going, what will they do? Because neutrality I want to hold. Because charge neutrality is a concept. So what should I do? I must see that the recombination takes place. Okay. So carriers are trying to diffuse down, okay, and recombination is trying to remove them. So what will they create? We have seen earlier excess carriers decay in space. Okay. So there will be a gradient set in of hole distribution in the N side and electron distribution in P side. Once gradient set, which current start flowing? The diffusion current, dt by dx, dn by dx. As soon as I say, so I have Jn diffusion and I have Jp diffusion. If I know my diffusion net current, Jn plus Jp, I always said opposite direction, sign wise, they will add, therefore total current will be J diffusion current. Now this essentially means from where these carriers will keep coming then, because they will be collected. So which one will provide the carriers? The battery. You have a source of this ions kept the charge battery there. So this current flow in the external circuit is supported by the battery. As soon as you remove the battery, it will go to equilibrium and no current. The battery keeps supplying those charges which you want for steady state carriers to keep moving across the junction so that the barrier potential now remains V0 minus, yes. This means there will be a current flowing in the PN junction. Is that clear? Now this current is what we call diffusion current, but to do this, if I look at this depletion region little closely, on this side let's say, the holes which are coming here, and as I said, no carriers recombine in the depletion region. I said it, okay, there is everything is free for that. As soon as it reaches, it starts decaying. Towards which value it will decay? Its equilibrium value. If this is my P, this is my N, and these holes which are P's of N, whatever is P's of N0, that is equilibrium value, carriers, because they will diffuse and recombine. We have already done this theory, so they will start diffusing and recombining and will finally reach its equilibrium value. But this profile will be maintained. Why? Because battery will keep supplying you charges, so that this similar argument, if electrons are less or more here, they will be reaching NP. Call it NP at minus XPO, this is PN at XNO. Nothing in the phase charge. From here, they will decay to NPO, here they will decay to PNO. If I know the gradient, then what will happen? I will find this diffusion current, APX, I can find JNX. Before we evaluate this, now the question arises something else. Beyond this value when it reaches NPO, let's say this, to show you here, it's something like this, but there is still a semiconductor here which is charge neutral. Is that correct? But the polarity will pull these carriers to the other end. What does that mean? If there is a charge neutrality, what is the electric field there we say? Electric field is 0. That's what we say, charge neutral. However, if there is charge neutrality, how this carrier reach the contacts? So there must be some electric field in the P region as well as in the remainder of N region, which will take these carriers to its logical end, to the contact. This means there will be a drift current after the diffusion current, which will be exactly equal to this, to pull it out. Otherwise, the carriers cannot reach the contact. However, this electric field has to be very close to a very small value. Why? Because otherwise neutrality condition is violated. So this is called a paradox. In assumption we say E is 0, but in reality if E is 0, no current can be. So electric field exists even in PNN regions. There is no space charge, neutral hai na? But that means this additional injected carriers do disturb the neutrality very small way, creating some built-in fields in the PNN region which actually pulls the carriers towards the end of the contact. This is very important. This is a paradox, and you keep telling E is 0 in calculation, and suddenly you say, oh, if E is 0, how do I get the carrier? Okay, don't worry. I say, okay, very small field, treat it value as 0, but it will take carriers. This is something all ideality people do it. That's what I will also do it. Is that correct? So I must now, what is the next step for me? I must evaluate the dpdx or pnx and npx, and if I derive that expression, then I can write j is equal to q dp dt by dx minus q dn dn by dx. So I know the curves. Is that method clear? What is my procedure? Procedure is, I assume all this, I say okay, here everything is constant, I don't worry, I only say they will diffuse down, recombine, and which equations, since there are excess carriers, which equation they will follow in steady state? Continuity equation. But in steady state, the time dependent term is 0. Then I have a space dependent term for me, so I can always calculate the discharge, dp by dx or pnx. This is the technique which I use. Okay, so let's, because to solve any differential equation of second order, even if it is simple, what I need? boundary conditions. Even if I make dN by dt 0, dP by dt 0, I don't need initial condition, but at least I need two boundary conditions because it's a second order differential, so I need two boundary conditions. So the first thing I must do, in this case, what are the boundary conditions? One you can see from clearly here. As you move away from the junction, the carriers go towards equilibrium value. So we say at x is equal to infinity either side, PN is excess carriers go to equilibrium. So एक boundary तो हमेशा common से. So one boundary is always there. The second boundary which I am interested in, how to evaluate this? So I don't know this value. At x is equal to xno and x is equal to minus xpo, I must get some value. And this value I can probably get from this kind of relation. Because what does this essentially mean? You can say on the P side, you are Na, let's say on the P side it will be Kt by Q, ln P's of Po, and what will be Ni square by Nd? N's of Po. Is that correct? Oh, sorry. Ni square by Nd is P's of P. Sorry, very good. So I anyway see P's of Po can be related to P's of No. Now if I say whatever is happening here is constant, so whatever is here is same as here. Now if I know this value, this is anyway getting related. Okay. So I say okay, so is this the value same? If not, how much is different? So I will assume they are same, but if not, I may have to really modify. Is that clear? But otherwise this boundary is also clear to me. If I know this value, I can also say this is the same value. So relationship between this and this I can get at this value, therefore I know how much is the P's there. Once I know these two, I will be able to solve second order differential. The two equations, second order equation 2 BCs, so I can have 2 BCs. And once I have 2 BCs, Pnx and similarly Npx can be okay. So let's start doing 2 minutes. Maybe this expression will derive. At least BC will derive. So this can be written as PNO is equal to PPO. What is PPO? What is PPO? The whole concentration in equilibrium on P side, which is equal to what? Na, which is equal to Na. This is e to the power minus QV0 by KT. This one relation is important. Okay. Then I derive another expression. This is under equilibrium. We only derive this equation, it's dropped, don't worry. Under forward bias, what is the built-in voltage now? What is the barrier potential now? Earlier it was V0 in thermal equilibrium. I apply. So how much is the barrier now? V0 minus Vf. So by same logic, I say P's of T at XPO at this value divided by P's of N at XNO here at XNO is equal to e to the power Q V0 minus Vf by Q. Now my assumption which I said, my assumption is PP0 is P's of T at minus X. What is this assumption is trying to say? That whatever is here is same as here. In reality this may not be. There is some diffusion is there, some recombination close to that may occur, so they may not be exactly equal. But our assumption is P's of P0 is equal to P's of P at XPO. If this assumption is made, divide these two equations and I get this relation. P's of Please remember what I did. This is under forward bias, this is under no bias. Okay, I divide the two equations and use this relation. P is of PO is P is of P at minus XPO. So the relationship I am going to get PN at XNO upon PNO is equal to P to the power 2VF5. एक term cancel हो जाएगी. If I use this and this PPO can be cancelled. Therefore, I will get P's of N at XNO to the P's of NO is. So, what does this physically mean? Baba? P's of at XNO means this point. This is PNO. So, what does that mean? This concentration is raised from its equilibrium value by e to the power applied QVF by KT. By similar argument, what should be the other side? N's of P at minus XPO divided by NPO is also equal to e to the power QVF by KT. So the electron concentration on the P side will rise from its NPO value to the e to the power of that. Same way, holes on the N side will be exponentially by voltage will rise to e to the power q. So now I have boundary conditions available. This is constant. This I know how much I apply. P XNO and N the P of XPO. This boundary values now I know. And what is the second boundary condition? At x is equal to infinity on minus side or plus side, the PNs will be always PNOs and NPOs, the equilibrium value. Two boundary conditions are derived. Now I can solve the second order differential equation with these two conditions and find Pnx. Is that clear? That's tomorrow. From here, is that anyone has a doubt? Quickly see, because this is how all device physics is all about. This is where we actually find out relationships. Math. Is that okay?